I'll explain how to generate photorealistic images of yourself using AI. This will allow you to generate more creative photos without having to do a photo shoot every time. Whether you're a marketer creating ads, a business owner building a website, or a YouTuber making thumbnails, this is going to save you a lot of time and a lot of money. It will take about 15 minutes and 3 steps. First, we'll download what's called a diffusion model that can generate images when given a text prompt. Next, we'll take just 5 of your photos to fine-tune or train this model. Lastly, with the knowledge of your photos embedded, you'll be able to generate new images in any environment. By the end of this video, you'll be able to generate high-quality photos of yourself without the time and cost of a photo shoot. And further, if you stay for the second half, I'll explain the technical details of how these diffusion models work. And just as an appetizer, here are 2 photos that I generated earlier. Here's myself up on a horse, and this one here standing on a wind turbine. And these were created with just 5 photos used for training. So that's what I'm going to show you in this video. And let's go through a very quick overview. Oh, sorry, I'm messing my slides around today. First off, in the first half, I'll explain how to fine-tune in 15 minutes. So we'll generate some images without fine-tuning. Then we'll generate a data set with your photos. I'll tell you exactly what photos you should pick to get the best results. And then we'll do fine-tuning with 5 photos. Now, 5 is going to work, but probably you should go for 20 to 25 at least if you want to have something very high quality. But yeah, you'll be amazed at the results with just 5. And then I'll go through a little comparison of the performance after we've done the fine-tuning on 5 of my photos. Unlike most of my videos, I'm going to do the explanation at the end. I'll explain how diffusion models work. So what is diffusion? The way that these work via indirect diffusion. So actually we don't diffuse images, we diffuse what's called a latent space representation. And then I'll review some of the components in the model we're going to use today. It's a model called Flux from Black Forest Labs. I'll give an intuitive explanation to what the diffuser, the VAE, that's Variational Autoencoder, and the text encoders are, and how they all piece together to work as Flux Schnell or Flux Dev, the 2 models we'll talk about today. So before I go into this explanation, let me show you how we can fine-tune a model. And the model I'm going to fine-tune will be the Flux Schnell model. This is a fairly recently released model from Black Forest Labs. They have 2 variants available open source. They have Flux Schnell and they have Flux Dev. Flux Schnell is a faster model, and it is also a little bit lower quality than the Flux Dev model. Actually, both of these models are diffused, or rather distilled. Sorry, that's going to get confusing. They're distilled from a much larger model called Flux Pro, which is not available as open source, but presumably Flux, or rather Black Forest Labs, have trained the Pro model and they've distilled down these Schnell and Dev models. Just a quick other note that Flux Schnell is openly licensed. It's got, I think, an Apache 2 license. Yep. Whereas the Flux Dev model is only licensed for non-commercial use. So that's something to keep in mind, and part of the reason why I'm going to focus on the Flux Schnell model today. To get started with training, we'll need a GPU. You can train this in Google Colab. I'm going to show you training using a rented GPU, but I will walk through the steps that you need to add if you need to train in Colab, because Colab does not have as much memory if you use a free Colab in particular. So I'll show you how to get past that. To rent a GPU, I have a few recommendations. They're written in this repo here, Trellis Research One-Click LLMs. Right now, and this does change, the best for value, I would say, is running an A40 on RunPod. It's about 39 cents per hour. However, if you need higher VRAM, which we don't, 48 gigabytes will be fine for training Flux. If you wanted larger, like 80 gigabytes, I'd recommend an A100 from Vast AI. It's about 80 cents. That's significantly cheaper right now than RunPod. And then if you really wanted high speed for inference, you should use maybe a H100, which allows for FP8 inference in a very efficient way. So for now, I'm going to run on the value option, also probably the best UI using RunPod. And I'm going to use a one-click template for fine-tuning. So underneath the RunPod one-click templates, I'm going to select this template here. This will bring me to a screen where I can pick a GPU. I'm going to pick that cheapest one, the A40. And you'll notice that this fine-tuning notebook by Trellis pops up because I've clicked on that one-click link. And then I'm going to click deploy. Now I've already deployed a little bit earlier just to allow the pod to start up. So here is the pod, and I'm going to click connect and connect to Jupyter Lab here. Just a note that if you do want to use Vast AI, you can scroll down in the one-click templates and you'll find a one-click fine-tuning template for Vast AI as well, which helps support the Trellis channel through an affiliate link. So here I'll connect to Jupyter Lab. And once I'm connected, I need a notebook that's going to allow me to generate images, and it's going to allow me to do the fine-tuning. And yeah, this is quite a popular thing to do, fine-tuning images. So there are a few quite good libraries available, one of which is AI Toolkit by Ostris. And this repo here, which you can check out yourself, allows you to fine-tune via scripts. It allows you to fine-tune actually via a Gradio UI, and it also allows you to fine-tune via notebooks, which is what we're going to do today. And it gives you some tips on inference using things like Comfy UI. So here are the notebooks. If you want to access free notebooks, I recommend these. And these are going to mirror a lot of what we're going to do today. I have basically taken inspiration from these notebooks here, and I've made some updates for those who have access to the lifetime Trellis Advanced Vision repo, which is this one here. If you would like to buy access, you can go to trellis.com/advanced-vision. So in this Advanced Vision repo, which also contains fine-tuning for multimodal models, we're going to go to the Flux section. So let me just go back here. I'm in the base Advanced Vision repo. It contains fine-tuning for multimodal models and now contains fine-tuning for Flux. If I go to the fine-tune folder, and then I go to Flux, my photo's in my way, then I'll see here this notebook, Trellis Flux Inference and LoRA Training. And this is the one that I'm going to upload and walk you through now for doing inference and fine-tuning. So I'll click on Upload here, and then grab this Inference and LoRA Training notebook. And now with the notebook uploaded, I'm going to start running the installation. This command here just tells me what GPU I'm connected to, which is kind of nice if you're running locally in particular, just to check GPU is connected well. I've got the NVIDIA A40 here, and I should have 48 gigabytes of VRAM. Not sure if that's written somewhere. I think there's 46, so it's got 46 free out of 48 maybe. Next, we're going to clone this Ostris AI Toolkit, and we're going to create a folder for the dataset. Yeah, if this is going to be run on Colab, you actually want to use content rather than workspace. But on RunPod, we're going to be working inside the workspace folder. And this is where we're going to put the dataset. So you can see in here, that's where the dataset for fine-tuning will go. Now, in the meantime, I'm going to initiate all of this installation. And next, I'm going to set a Hugging Face token. The reason for this, well, two reasons. One is you need to put in a token if you want to push models up to Hugging Face Hub, which is something we're going to do. But also you need one if you want to access the dev model, because it's a gated repo and you need to accept access. Now, we're not going to train the dev model today, so that's not an issue. But if you did, that's another reason for needing to put in the Hugging Face access token. So I'm going to run that. And once the installations are done, it will ask me for that, and I'll put in my Hugging Face token, which you can get by going to Hugging Face Settings Tokens. And usually I'll set one up, and often I'll just invalidate, refresh, copy it, and put it into my notebook over here. So while we're waiting for install, let me talk a little about dataset. So when you're picking your photos, and I'm going to include 5 of my photos, you want to have, for high quality, probably at least 20, 25. But you can get away with 5. And I highly recommend putting in one of a full length body shot, because if you don't include your body, then your body kind of provides context for the shape around your neck. It also helps the model just to get a holistic sense of you as a person. So I would recommend having at least one body shot in there, as well as headshots. I recommend having high quality images. Seems like a standard recommendation. And also maybe don't have too many of them with multiple people. It's probably fine to have some with multiple people, but the majority should be just you on your own if that's what you're trying to fine tune towards. Okay, so I'm going to go to dataset, and I'm going to upload a series of photos. Now you'll see I'm not just uploading 5 photos, I'm uploading TXT files as well. We can take a look at what's in those TXT files. In the meantime, my Hugging Face access token has just been set, so that's working well. So let's take a quick look at the images, and you'll notice here the format. So it doesn't strictly have to be image 1, image 2, but you do need to have a matching name between your image and between the text file. So I've got image 1 here. Let's see what this is. Okay, this is me here getting out of a boat or onto a boat. And you can see the text where I've got climbing out of water. So in the caption, you want to put something descriptive. You can put in things that are going to be comma separated. So Mediterranean. Is that how you spell Mediterranean? I'm not sure if there's 1 or 2 D's in that. There's just 1. So you want it to be comma separated. And also I recommend putting this here. So this is square bracket, trigger, square bracket. And this will be automatically replaced during training with what's called your trigger word. And the trigger word in my case, it's going to be Ronan trellis. And what this does is it trains the model that if it sees this specific trigger word, it will generate in this specific manner. So later when I generate images, I'm going to use that trigger word as well, Ronan trellis, standing on a wind turbine. And it's going to know then to use the training aspects that I had incorporated. So let's look at this second photo here, and I'll just save that modification. So here's me, just a headshot and the text. So trigger headshot in Indian attire. And this one here, this is me just standing, wearing a suit in a gray suit and purple bow tie. Let's take it this one. Me playing accordion. So playing the accordion. And this one here, oh wow, that's pretty large. It looks like it's just me relaxing. So yeah, trigger relaxing. So yeah, these are the 4 photos. You can see I've one that includes, it's not a full length. Is there the full length body shot? Yeah, so this is like partial, and then there's the other one as well. So this is enough information to give a sense of my whole body. And you can see how I've set up the captions in this same folder. So with that, we're in good shape to start off the fine tuning. But first, I'm just going to show you how we can do some inference. So we can just run a generic prompt. And we'll do that by loading the model. And I have a few comments to make here with respect to Colab. So just to set the stage, we have now set everything up. We've got the data set ready. What we're going to do is load from Hugging Face this Flux model here. So it'll be downloaded. And I'm going to show you how to generate an image with the model that has not been fine-tuned. So we'll start off by importing diffusers, or rather this pipeline from the diffusers library, and importing torch. And then we're going to load the model into the pipeline. Now, if you watch some of my other videos on text or language models or speech, you'll often see that we load a model from pre-trained. We're just loading one model. Here we're loading a pipeline. And the reason is because there are multiple models within this model. There are models that convert the text into vector representations. There's the diffusion model, and then there's a decoder that will convert from a vector representation of the image back to the image. I'll talk more about that later, but the reason we're using a pipeline is because we need to load multiple models at once. So we're loading these models in, and we're specifying loading in bfloat16. This is a 16-bit format. It is not supported by the GPUs that are free in Colab, so we'll have to adjust for that later if we use Colab. If you're using the GPU like I am now, an A40, you don't need to run any of these commands here because you'll have enough memory and bfloat16 is supported. If you do not have enough memory, so you need basically to run the model, maybe you have 24 gigabytes of VRAM instead of 48, you might want to uncomment this line here that says enable model CPU offload. What this does is it will run any calculations in excess of the GPU VRAM you have on your CPU. It'll be slower, but it will still work. Further, if you want to run on the free Colab, you need to take some more drastic steps. So you need to enable sequential CPU offload. You need to enable some slicing and tiling of the VAE. And you also need to move the format, the data type rather, from bfloat16 to float16, which is a simpler data type that is supported by the T4s on Colab. So uncomment these if you're on Colab, leave them commented if you're not. And this one here, if you're running locally, maybe on a 24 gigabyte GPU that does support bfloat16, you can run this to make sure that it will run and overflow onto CPU. Okay, I don't need any of these because everything will fit. So I'm just going to load the pipeline and move it onto CUDA, which means moving it onto GPU. And I think you probably need at least 32 gigabytes of VRAM to do this. Now, the last line here is what allows you to load a LoRA on top. A LoRA is an adapter. So you can think of having loaded the basic pipeline, and now we're going to load in an adapter or a modifier. And that modifier will contain information from our training images, and it will adapt the behavior of the base model to perform and produce images that look like me. Now, we haven't trained that adapter yet, so there's no point in loading it. So I'm just going to load the base model here. And once the base model is loaded, it will take a moment. You'll see the weights download. I'm going to run inference. And running inference means taking in a prompt, which is this prompt here, and generating an image. Now, you can see in this prompt, I've provided my trigger word, but that's not going to do anything yet because I haven't applied the adapter or modifier yet, and I haven't done the training. So when I just take the off-the-shelf model, it's of course not going to know that this should be a trigger word. So we're going to generate an image and save it as snooker close-up base. So I'm trying to create an image of myself playing snooker. You can see, by the way, the downloading is happening here. We'll talk through the different pieces later on, but broadly speaking, there are a few models being downloaded to convert the text prompt into a vector representation. There's a T5 model and a clip model. The T5 model is actually quite large. It's this one here. The clip model is not that large. It's this one here. And then we have the diffusion model itself. It's a transformer. It's what basically takes in the text commands and converts to an image. And that's this here. It's about 14 gigabytes in size. And then we have a VAE. A VAE is a variational autoencoder that converts a vector representation of the image we generate out to be the final image. That's typically taken off the shelf. All right, more on that later on. In the meantime, looks like the model is loaded, and we're going to run inference here. Now, let me just check which model I loaded. Yep, looks like I loaded the Schnell model. And here we're going to generate. Now, it looks like I've actually got 28 steps of diffusion. That's probably a lot for the Schnell model. You typically would do only 4. Generally higher can give better quality, but it's slower. So let's see what this gives. Okay, so here's the image. And yeah, pretty good stuff. I wish I knew easily how to zoom out. Can I just zoom out this way? Okay, nice. So yeah, you can see the image quality is good. Snooker is a tough one. That's why I'm giving it. I love a bit of snooker. I used to play with my granddad, and clearly there is not data about snooker because the cue is not in the right position. And I do not recommend this strategy here of having one hand on the table and using the middle finger. That's not a recommended snooker strategy. But gives you the sense of how this model performs as a base. That did not look like me, which makes sense. It's just a base model of somebody playing snooker, a man rather, playing snooker. So with that, we're going to move on and we're going to do the fine tuning. And we're on to the fine tuning setup here. So there is a configuration that we need to do. If you're running this in a scripts approach with AI Toolkit, then you will do this via a YAML file. But we're going to do it just here in a cell. So let me zoom in here. Now, there's not all that much you're going to need to change. You can give a custom name here to the folder that we're going to generate. The output folder is going to be workspace. If you're in Colab, you want to swap that to content, but we're not, so we're going to leave it like that. This here is around logging, so we're going to log performance every 50 steps of the training. We're going to use a GPU. Now, here's the trigger word. So you want to define your own trigger word. I recommend using a word that's not a word. So you don't want to do something like, Ronan trellis, because that's going to have some meaning in the background. The model will already have meaning subscribed to probably the name Ronan, maybe not trellis. So make a compound word that's not a word really. Next up is LoRA. This is the specification of the modifier, so the adapter. I should emphasize that if you haven't seen some of my previous videos where we do a lot on LoRA training, LoRA is an approach that says, okay, we're not going to update the whole 12 billion parameters. What we're going to do is define an adapter with many fewer parameters, like maybe a few 100 million, and we're going to train that and stick it on to the base model to affect its performance. And yeah, mathematically, it's a low rank representation. That's why it's called LoRA. So here are the parameters. Yeah, I recommend for a low number of images, probably 16 or 8 is a good choice for the LoRA's rank. That's the number of rows in the matrix of the adapters. And linear alpha, yeah, it's 16 by default in AI Toolkit. I think you probably can go a little bit higher with this. This affects the training rate, so it means that your parameters are updated more aggressively if you put it higher. If you're going to train with tens of thousands of images, which I think is really too much, probably at most you want to do maybe thousands, then you could use a rank of maybe up to 128. And just note that if you increase your rank, you should be training at a lower speed. So you need to reduce the value of alpha, not quite proportionally, actually proportional maybe to the square root. But anyway, if you go for 128 for training, say 1,000 images, probably you should reduce your linear alpha down to something like maybe 8, for example. All right, so here we're going to define the precision to save. I have that as float 16. bfloat is generally a better data quality. It keeps more of the 16 bits for the exponent rather than the mantissa. So it's able to cover a much larger range. Like say it can cover from, this is not exactly the numbers, but like 10 to the minus 10 to 10 to the plus 10 instead of 10 to the minus 5 to 10 to the plus 5. So it covers a much larger range. So yeah, we can go for bfloat. This is how often to save. That's fine. It'll save at the end anyway, which is important. For the data sets, here you need to specify the folder. This will be content again if you use Colab. You can see here there's some options. I mentioned that you want to separate your keywords with commas. That's because if you do that, you're able to shuffle the caption order split by commas. Shuffling the order will just make the model learn in a more generalized way. For 5 images, it's not going to make a difference, but if you have larger images, you should do that. And yeah, I wouldn't change anything else. Caption dropout rate. So it's going to do some training where it doesn't provide any caption, and that will just generally ingrain that type of image into the encoding of the model. Again, with just 5 images, setting a dropout of 5% doesn't even make sense because 5% of 5 is less than 1 image. Okay, so here for training parameters, the batch size. Yeah, I would recommend using 1 unless you have at least probably 32 images. Then you could go up to maybe a batch size of 2. If you have 1,000 images, you can move towards batch of maybe 16. Also, if you increase batch size, it's going to take more memory, so you need more VRAM on your GPU. If you see CUDA out of memory, then you need to reduce your batch size. Total number of steps in training. So the AI Toolkit recommendation is 500 to 4,000. I think that's a lot. And I prefer to increase alpha, which I did to 32, and use a lower number here. Also, yeah, I think generally what's happening here, and this is a more advanced comment, is that we're actually overfitting the model to some degree. So when we would do fine tuning on text, we would rarely train for this many steps. If I have 5 images for 500 steps, that's literally showing the image 100 times to the model. So we are very much ingraining that into the model, and it's going to fit that very exactly. That would result in overfitting and poor generalization in text models. But this seems to be a good approach for fine-tuning image models. Next, we can choose what we're going to train. So as I said, the pipeline is actually multiple models. It's got the text encoders. There are actually 2 text encoders in Flux. Then it's got the diffusion model, which is a transformer, and then the VAE. So here we're saying true, let's train the UNet, which is the transformer itself. This is like the secret sauce of Flux model. And you can also choose to train the text encoder, but I don't think it would improve performance that much more. Would it work with Flux? I'm not actually sure. Gradient checkpointing. you can set this to true. It'll save memory, so I'd recommend saving that. It means that during the forward pass, you don't save as much information for the backward pass. Because you don't save that info, it reduces your memory requirements, but it's going to result in using more compute. But we have lots of spare compute, so generally we will leave that on to true. Okay, learning rate is an important parameter here. 1e minus 4 seems to work. You can generally, you can play around with this value, maybe make it a bit lower if you've got more data. That will allow you to kind of more slowly update according to the amount of data you have. The script is going to run samples, so it's going to run samples at the start, unless you set this to true, which I have. I don't want to waste time generating samples at the start, but it can be good as a baseline just to see how a specific image looks without the fine-tuning and then with the fine-tuning. You can also completely disable sampling, which is an option here. And I haven't looked into this Vel curved weighting, so I'm not going to comment it in here. EMA is for smoothing. I would just leave that to default. And then this is the torch D type. It needs to be, it can't be BF16. It has to be float 16 if you're going to use GPU on Colab. Next, we get to the base model we're loading, which is the Black Forest Labs Flux Schnell. And we're going to define here the LoRA. So this is kind of a base LoRA adapter that we're taking from the Ostrich path on Hugging Face. Yes, it is a flux model, and we are actually going to use quantization. So the backbone of the model, the core weights, we're actually going to load them onto the GPU in reduced precision. So they're going to be reduced to 8 bits. That will save memory. I think you probably can run this on 48 gigabytes by setting that to false. But I don't want to risk running out of memory, so I'm going to leave it to true, and the quality is fine anyway. Next, you have some options here if you want to use low VRAM, but it is going to be slower. Okay, so moving on to the samples, we're going to have sampling every 250 steps. So that means it's going to generate the samples halfway, and then at the end, it's going to generate samples that are square, 1024 by 1024. And here are the samples that it's going to generate. And I recommend putting in the trigger and then putting in these prompts here. You should customize these to the types of images you want to generate. And yes, you can either generate them right at the start by commenting this out. I've uncommented it, so it's going to skip the first images. And then it's going to generate at start at 250 and then at 500. So you'll have 3 sets of images to compare. We're going to have 2 sets because I'm skipping the first. Everything else here, we're going to leave as is. There is this concept of guidance I'll talk about later on, but Schnell doesn't do this. It's basically combining running a diffused image without a prompt with running diffusion of an image with a prompt. So this technique can improve performance, but it's not something that Schnell does. So guidance is set to 1, which means there basically is no guidance of the model by a separate generation. And for sampling steps, as I said before, Schnell is, well, I don't know if I said this, but it's designed for 4. It's distilled for 4 sampling steps. So that's why this is set to 4. And yeah, here you can add any more metadata. All right, that took me a while, but hopefully gave a few insights on the details of the fine tuning. So we're going to set that configuration, and now we're going to run the job. So we'll see things getting set up. There are a few warnings here that I'm not too concerned about. We've got the configuration being printed out, and looks like here I have run out of memory. So kernel, shut down all kernels. And the reason is because I already ran inference at the start of this video, so that model would have been loaded, and I was probably trying to load again on top of a model that has already been loaded, so it would run out of space. So let me just go up here and make sure because I restarted my kernel, I do need to rerun these cells. So I need to put back in my Hugging Face token, although that probably would have been set in environment, so that would have been fine. And now I need to set this and run the fine tuning. Okay, so the job is now running and we have the configuration printed out. and this is still ongoing. So I'm going to just talk about how you might want to set up logging. One thing I did kind of glance over in the configuration is that we have turned on logging here. So I've set up a logging directory called logs, and I've set up logging to be every 10 steps. So this here is going to appear in our workspace. So you can see now we have logs, and there's going to be a training run. There's the one that failed, and then there's this one here that's running. And we have this events log here, which you can't just open up and see. Unfortunately, you need to have software for that. But we do have the software, and it's called tensorboard. So what I want to do is install tensorboard and then set up a server that is going to provide a view of what's happening on tensorboard. So I can show you how that's done while the model is loading. The easiest way is to go to run pod, click on connect, copy this SSH command here, and now head over to either VS Code or Cursor or some other software you're using for coding, and click connect to host. Add a new SSH host like this, press enter, add it to the config file like this, and click connect. Now you can optionally do this via a terminal, so you could literally just copy paste that SSH command into a terminal. Something like, I won't open up a terminal, but you could copy paste it in. What's nice about doing it in VS Code or Cursor is that it's going to allow me to do port forwarding. And port forwarding means it's going to allow me to show on my local screen that tensorboard. So let's open up the folder. I'm just going to open up workspace like this. And now I need to view the terminal. And I'm going to install tensorboard with pip install tensorboard. And once that's installed, I can optionally make the upgrade to pip. Once that's installed, then I should be ready to run my tensorboard server. Just to note that it's not going to be useful to run the tensorboard server until we have generated at least one log, because if there are no logs, tensorboard will not show you anything. So I can run tensorboard like this. Let's head over. Let's head over to my server. When I run this command, it's going to bind to the 6006 port, which it is now port forwarded locally. So if I hold down command and click on that, it's going to pull up tensorboard. And let's see. We don't have any dashboard showing, and that's because the model hasn't saved any checkpoints, or rather hasn't saved any logs just yet. So what I'm going to do is let this run for a bit, and I'll come back once we've got the training done, and we can run through some more inference by loading, this time, the LoRA on top. Okay, so I've just waited now for that training to complete. Let's see exactly how long it's taken. Looks like a total of 25 minutes. So I was actually wrong. 15 minutes is a bit ambitious, although you could adjust that based on the number of images and the strength of your GPU and the types of quantization you do. So everything is now saved, and in the output folder, I should be able to check out the images. They're present within the samples. You can notice as well that we have a copy here of the safe tensors. This is the 250 sample point, and this is the final sample that's been created here. Let's head into the samples, and you can see I've got 5 samples at the 250 steps and then 5 samples at the 500. So we'll be able to compare how these look. So here's me. I love prompts. Definitely looks a bit more like me. Let's see then at 500 steps. Okay, so this one here now is definitely starting to look close. So maybe I need a few more data points, but definitely on the right track here. Could be worth looking at going up to maybe 1,000 steps if I want to improve that further. Let's take a look at some of the others. So here, not particularly good at all. I don't know how much that has me in it, maybe a little bit. Whereas this one here, starting to get the beard, the hair a little bit. Maybe not quite the right body profile, but maybe I could do it a little more photo. No idea why in the background there's some kind of fire. That's kind of interesting. Step 3, okay. So here you can definitely see some aspects of my facial features. And this one here now, it's starting to get pretty close. Just 2 more photos to go. So here, surfing, yeah, you can see it's starting to get towards me. And now this one's pretty good. So I like this one. I'm going to see if I can save this image, and I'm going to use it as a thumbnail for this video here. So these are the images that are generated automatically during the training process, because that's how the training process is being set up. So let me show you one more step, which is how to take your adapter and now run inference with it. So for this, you're going to need the adapter to have been pushed up to hub. Let's just check here. So it looks like we have saved the model. I haven't pushed it up to hub. That's something you could do if you like, but it's been saved here in the sample in the Ronin Trellis A40 as saved tensors. So let's head back up to the top of the script here and do kernel. I'm going to probably shut down the kernel at this point. It's possible that the model is still pushing to hub. Let me just see if there is a command. Yeah, I actually don't think there's a command that is going to push this to hub. So you would have to write a snippet of code if you want to do that. So what I'll do is I'll update the script afterwards, and I'll just put in a little addition to the configuration file here, so you can optionally push to hub if you decide that's what you want to do. In the meantime, there's nothing to stop us from running inference. We will just restart the kernel here. So actually I'll click kernel restart. And now I'm going to have to make sure that everything is properly uploaded, which it should be. And the one change I'm going to make is now to load the LoRA weights. By the way, if we just click here and show file size, you can see the LoRA is 164 megabytes. So pretty small compared to the model, which is over 20 gigabytes. And here we're going to load the LoRA weights from output, Ronin Trellis A40, and this is the name of my weight. And what this is going to do is take the base model, load the base model, and then apply that adapter or modifier to it. It should be fairly fast because we've already downloaded the base weights earlier on. And it looks like all the shards are loading. And once that's all loaded, I'm going to run the man playing snooker. So let's see how this goes. And it should save them back in my workspace. And I'll just add here, it's generating right now. 28 steps is what I've set. You can control the height and the width of the image just by adding those parameters here. And you can also check out Hugging Face if you want to check the other parameters you can set in the pipeline. For example, the number of generation steps, if you're interested in that. Now, it's possible here that because I'm doing more steps, it's going to generate better results than the 4-step sampling that would have been done in the samples that were made during the training. So let's see. I unfortunately have overwritten my previous file. I should have called that something else here. That's okay. We can take a look here. Yeah, so this is pretty good here. Like, definitely starting to look like me. Maybe the eyes are a tiny bit off, but pretty close. Obviously, this image model is not able to play snooker, but it knows that I have a good audience, so I appreciate that. And this brings us to the end of the fine-tuning demo. You can see we've gone all the way from creating a base data set to then inferencing the model to then running the model with the LoRA adapter applied. And now, if you want to stay around, I'll describe a little bit what's happening here under the hood with these Flux models. Next, we'll move to an explanation of how these models work, and any terms you didn't get in the first half hopefully will become a bit clear. I'll start by explaining how diffusion works, then I'll explain how you actually diffuse latent representations. These are basically vectors or tensors that represent the image. So that's what the transformer generates. It's kind of a vector, and then that vector is converted into an image using a decoder, which I'll talk about. Before that though, some basics on how diffusion works. So here's how you train a diffusion model. You start with a set of images, maybe millions, hundreds of millions of images like this one here. And you add noise to each image. So you add some random noise, some Gaussian noise. and you feed this noisy image into a diffusion model along with a brief text description. So here, Dr. Seuss cartoon, and you get the model to predict some noise. So the model will try and predict this Gaussian noise, and you compare what it predicted to the actual noise that you added, and you use that comparison to update the weights in your model here. And by the way, there's a whole history of what types of models you should use here, like ResNet or these recursive nets or convolutional nets. But it turns out transformers work very well. That's what the Flux model uses. So you can think of this here as a transformer, not just think of it. It is a transformer, and it's trained by basically predicting noise and comparing those predictions to the actual noise that was added. So at the end of this training, with hundreds of millions of images or more, you have a model that's able to predict the noise if you give it a noisy image. And so it's capable of taking in some kind of noisy doggy image here, along with dog cartoon, and predicting the noise in this image. And of course, if you can predict the noise, you can take the noisy image minus the predicted noise to get a clean image. So this is the idea of how diffusion works. And in fact, you can take it all a step further to the point where you literally start with pure noise and you give it text that will say dog cartoon. And in the first step, it will predict a small amount of noise removal to get to this. And then you take this noisy image and repeat it, and you predict what noise is here, and then you get to the clean image. Now here I've just shown 2 steps. Typically it's more than 2. So the Flux Schnell model uses 4 steps. So we'll start with pure noise and come out to clean. And then FluxDev will use 20 or more. And often more steps means you get a better quality final image, but it's also slower. So this is how diffusion works. And the next level to understand is actually we don't directly diffuse the models. We diffuse representations of the model. So just like in my language model videos, I'll talk about how a word or a token is represented in high dimensional space by an arrow. So like an arrow in 2048 dimensional space. Well, that's kind of the same with images. We actually work with images as tensors or vectors, multidimensional vectors. So you can think of an image as some arrow within very high dimensional space, and that's called latent space. So we work with these images in latent space representations. It just means we represent them as these arrows. So actually, we're not diffusing noise like an image's noise into less noisy. We're actually working with an arrow that represents noise, and then we're removing noise in that high dimensional space to get a cleaner arrow, and then we get the final clean arrow. And once we have the final clean arrow, we convert that into our image using what's called a decoder. So that's the next thing to explain. It's decoders or variational autoencoders, VAEs. A VAE is able to do both directions, so it can take an image and can encode it into a latent space representation. By the way, there's a good podcast, Latent Space, it's called, recommended. And that's why it's called Latent Space, is because it talks about machine learning and latent space that is relevant in vision models. Anyway, a VAE will take an image and encode it into a vector like this, or a tensor. And it can then also decode, if you give it this vector, back to a clean image. And if you're interested, the way that you train a VAE is you start with a set of images and you train the model so that it can suck the image in, create a latent space, and then reproduce that same image. So you test whether it's capable, if given an image, to reproduce the original image. And the way you constrain that generation is you force the latent space representation here to be Gaussian. So you force a specific format for the representation. You force it to be represented in, say, 64 multiplied by 128 dimension tensor. So you're forcing this numerical representation, and you're forcing that general shape to be a normal distribution. So if you force it to represent like that in the middle, you then test whether it's able to get to that middle representation and back again to the clean image. And where you use this variational autoencoder is in 2 ways. You use it when you are running inference. So by the way, this whole thing here, these 2 pieces, that's the variational autoencoder. And you use it in 2 ways. You use it during generation or inference. So during inference, you take noise or noisy image, you put in the text, use the diffusion model to predict that noise, and eventually get to a representation of the image. And then here's where the variational autoencoder will take the representation of the image and actually give you the image. So yeah, basically the whole diffusion process happens in latent space, and only at the very end do we decode to get that final image. We also use the encoder part during training. So during training, we're going to take a noisy image, we're going to put it into the diffusion model to calculate a latent space representation. And by the way we do that is technically we predict the noise and then we subtract the noise to get this representation here, and we compare it with the representation we get from the VAE encoder. So here we take the clean image that we have for training, we put it through the encoder to get a latent space representation. And now that we're able to compare what our transformer produced with what the actual representation should be, we can take the difference and back propagate. So we can use that difference to update our weights in the diffusion model. And by the way, it's fairly common to just take this variational autoencoder off the shelf and focus on training this diffusion model here, because we're pretty well able to generate these models that can both go to and from real image to latent space representation. But what we want to do is improve on the diffusion model that's able to diffuse out these latent space representations given text prompts. So that's where the VAE is used. And so you can see at the very least, Flux or Flux Dev or Flux Schnell is going to have a diffuser, and it's also going to have a VAE. And so here we can put all of this together. So we have the diffusion model that's going to take in some noise initially, literally random noise, and it's going to take in some text here. So we want to generate a dog and a cartoon. Now, something I didn't show earlier is that the text doesn't directly go into the diffusion model. It goes via a text encoder. So this, again, can be transformer. The Flux model uses two different models here. It uses CLIP, which is an image and text encoder, and it uses T5, which is a language model encoder. So it uses two models to encode dog cartoon. It will then take in the latent representation, so the vector representation of this noise, and it will then try to predict the noise in order to get towards a dog cartoon image. So we'll go through one step of this to predict the noise to remove from this pure noise, and that will allow us to get to a cleaner image, or rather a cleaner latent space representation of the image. Then we repeat again. So we pass that image in. Again, we pass in the same text because that's what we're trying to drive towards. And we again predict the noise. And we do this how many diffusion steps we have decided upon until we finally get to a latent space representation of the dog here. So this is the way I'm representing the latent space representation of the dog, which at the very end will go through the variational autoencoder and it will be decoded to give a final clean image. So that's all of the steps of the inference. I'll describe now just a few advanced comments or more advanced comments on how the Flux decoder works. I've mentioned already how it has T5 and CLIP as the text encoders that go into a transformer, that's your diffuser, and then at the very end of many iterations of sampling, it will come back out through the VAE, which is off the shelf, maybe fine-tuned a bit. So a few general comments. I think I've said this already, but more diffusion steps generally gives better results, but it's also slower because you've got to run through the transformer multiple times. Flux Schnell uses 4 steps, it's fast. Flux Dev uses 20 plus steps. As usual with AI models or transformer models or neural nets, larger diffusion models or transformers give better but slower results. The Flux and the Flux Schnell and Dev models have 12 billion parameters, but they are distilled from a much larger model that presumably is over 50 billion or maybe over 100 billion parameters and is of higher quality. So if you have train larger models with more data, you'll get higher quality, as is commonly the case in neural nets. Now, I described a naive method of noise removal. So here I have a 2-step process going from this pure noise to slightly less noisy to clean. So that's a 2-step process. And here, in that case, I'm kind of removing like roughly equals amounts of noise, but that's not optimal. It's better actually to remove the noise exponentially. So you want to remove a lot and then kind of slow down how you remove the noise. And actually, even better than removing exponentially, you want to have trainable parameters that tell you for a given time step. So if you have 10 time steps, they tell you if you're at time step 1 and the image looks like this, then we should actually remove this amount of noise. So this is like dynamic noise removal. And one of the approaches there is called using flow. Basically, you train parameters that will give you a direction in which to remove noise, and that direction is ideally optimal for every given step. So this dynamic noise removal makes the noise removal more efficient. It's less naive than just, say, exponentially removing noise. And this flow approach leads to significantly better results. The last comment here I briefly mentioned in the first half is around guidance. The idea is that it can help when you're creating an image, let's say, of a cartoon dog. It can actually help to blend that with generation of an image that has no caption. This is called using guidance or guided generation, and it can help control the diversity in the generation you have. Now, there's no guidance in the Flux Schnell model. I haven't looked into detail exactly why or why not you couldn't try and add that. In the Flux Dev model, there is the ability to do guidance. So you can set that ratio up as far as 3.5. I need to look into the definition of how that ratio works exactly, but I believe it's a matter of blending your captioned generation with your non-captioned, although that may be more dynamically happening throughout the generation process. And that's how you can fine-tune a diffusion model in 15 or maybe 30 minutes to create any number of photographs without doing a photo shoot. Now, I've put a number of links below to free resources available online. And if you're interested in the exact scripts, you can go to trellis.com/advanced-vision. That allows you to get access, lifetime access to a repo with all of the multimodal and vision scripts, including ones I might upload in the future. If you have any questions on diffusion or suggestions for future videos on the topic, please let me know your comments below. That's it, folks. Cheers.